covers Griffiths E&M, section 2.5.2, induced charges. All right, so we discussed the rules of conductors before in the previous video. And we said that the electric field inside of a conductor is zero. Now, that electric field became zero because charges existed on the surfaces of those conductors, and that made sure that the electric field inside was zero. So let's talk about those charges a little bit more. I have a neutral conductor, so that is an uncharged, the same number of positive charges as negative charges, and I bring next to that conductor a positive charge Q. If I were to imagine what those field lines look from my positive charge Q, I'm just going to draw it down below. We know what those charges look like, or those field lines look like. They point radially outwards. So if there's going to be no electric field inside of my conductor, I'll draw that with blue. I know that my field lines from my conductor are going to have to somehow, be pointing in the opposite direction in some way, right? So the way that it does that, it's very hand wavy so far, is that it will paste charges on the right to be positive, charges on the left to be negative. Right? At least you can. I don't think I drew that perfectly right orientationally, but if charges on the right are positive and charges on the left are negative, we're going to get something that looks like this. Okay. Notice here that since there's a negative charge density on the left side, that there will be some attractive force between the conductor and our positive charge Q. Okay. So that's what happens when you have a charge outside of a conductor. What happens if I have some conducting surface, or some conducting volume rather, and I have a void or a cavity inside of my conductor that has a positive charge Q. Right, so there's some empty space inside of my conductor that has a charge inside of it. Well, I know that if I'm going to use Gauss's law to calculate what the electric field is at a point in space here, right, that tells me about the Q, the enclosed charge. So the way it stands, the enclosed charge would be plus Q, and then I would measure an electric field at this point, or at this Gaussian surface. But we know that we can't have an electric field inside of a conductor. So what happens here is that there's some distribution of negative charges that build up on that surface, so that if I were to evaluate use Gauss's law to evaluate the electric field at my surface, I would have no net charge enclosed. So now Q enclosed inside of that is zero, because it has my one positive charge and a bunch of little negative charges. Okay, but then my conductor, I didn't specify, but the way we first drew it was that it was uncharged. Now I'm generating some amount of negative charges along the inside of my cavity. Now my conductor has become charged. It doesn't make any sense. The only way that you can maintain to have these charges, the conductor be neutral, is for an accumulation of positive charges to also exist. All right. We know that from the rules of a conductor that the charges can't exist in the volume. They must exist at a surface, and we're left with two choices. We either have the outside surface or the inside surface. If they went to the inside surface, then they would cancel out all of the accumulated induced negative charges, so that's not the option. It turns out they all go to the edges of the outside. Now, the crazy thing about this is that if I do Gauss's law again, but now outside here, the charge enclosed is plus Q, right? All of the negative red and positive red cancel out, and I'm left with just the charge inside the cavity, even though there's no electric field inside of the conductor to kind of give that information across. Right. So then what's the field look like for that? Well, let's draw another example. I have some sphere. I have the center of my sphere here. I have some cavity with a positive charge Q here. We know where those charges go inside of the conductor. In principle, there should be the exact same number of each of those types of charges. I'm going to do the Gaussian surface outside. I get an electric field that is exactly like we would expect from a point charge, centered at the very center of our conductor, even though the charge itself is not at the center of its cavity, which is not at the center of the conductor necessarily. Pretty crazy. Okay. So you put a charge near a conductor, you generate induced charges. You put a charge inside of a void or a cavity inside of a conductor, you generate induced charges still, and those induced charges make sure that the electric field within the conductor is zero. But you can still have an electric field outside of your conductor too. Okay. So we're left with one more scenario that we have to talk about. What happens if I have a conductor that has a cavity? There's no charge inside of this cavity. Can there be a field line? Can there be an electric field inside the cavity? Okay, there's no charge, so the field line, if it exists, let's draw some more colors, has to go from one side. One field line has to go from one side to the other. Okay, and it has to be a closed line somewhere, and let's say that it's closed inside of our cavity or inside of our conductor. Okay, so I have some path that I'm going to follow along this electric field line. And we're just imagining that there exists an electric field line here. And maybe you say, well, we already know the answer to this, but you already know the answer, a part of this answer, this question. Okay, so I have an electric field. I'm going to walk along that electric field, and I'm going to take the integral as I walk along that path. Okay, in this case, my path is along the electric field specifically. I have to do that in two parts. I have to do one part of that path, which is the electric field inside the cavity. All right, that's the solid blue line here. And I also have to continue integrating the electric field in the conductor. All right, that's the whole path. That is the closed path. So to color code this, this is the solid line, and this is the dashed line. All right, but we know that the electric field inside of the conductor is equal to 0. And we know that the integral of closed path inside of an electric field is also 0. So I have that 0 is equal to this. Therefore, the electric field inside of the cavity must also be 0 if there's no charge inside.